In this video, I want to talk about vector database indexes, specifically how you can choose an index and some of the trade-offs between the parameters in specific indexes. There are a few vector indexing strategies that you could take. Indexes are data structures for extremely fast similarity search. And once you start working with high dimensionality or very large data sets, you start to have trouble with latency and memory, and that's what indexes solve. The two main types of indexes are flat indexes, which do a brute force search, comparing your query vector to all document vectors, and approximate search. And approximate indexes use data structures like a graph or an inverted file index in order to speed up search at the expense of accuracy. An example of a graph index is hnsw, or hierarchical navigable small worlds. For an inverted index, you could use IVF, or an inverted file index, or ivfpq, which is an inverted file index with product quantization. There are a few trade-offs to consider when you're choosing an index. Exact indexes are very precise. In fact, they're exactly precise, but they're slow on large data sets. But approximate indexes are faster, but they sacrifice a bit of accuracy for massive gains in latency and requests per second. Some key considerations when you're choosing an index are dataset size. If you have a really small dataset, it just makes sense to choose a flat index. It'll probably be fast enough for you and deliver perfect accuracy. And if you have a really large data set, an approximate index might make more sense. And then your accuracy requirements. Does your application require exact accuracy? In most cases, the answer is no, so you could use an approximate index. With an approximate index, you could still get 98, 99+% accuracy, but get massive speed boosts. Another thing to consider are your query latency constraints. What are your latency requirements? Is a flat search fast enough? Which index will give you a search with low enough latency for your application to work? A flat index is extremely accurate, but is slow. So it uses a direct representation of a vector embedding, which means it doesn't compress it in any way. And it does an exhaustive search over all document vectors. It's good when you have low dimensional data, when your dataset size isn't very large, when you're doing real-time data ingestion. You can ingest new data extremely quickly. When you have low query volume, if you have a large number of requests per second, flat index might not be ideal. And for benchmarking. So the thing about a flat index is that it gives you perfect accuracy. So you could use it to compare with your other indexes, which are going to be a little less accurate. So you'll be able to better know, okay, what actual accuracy losses you're getting with other indexes. An hnsw graph index is a graph index that uses nodes and edges to construct a network-like structure. And every single node is a vector embedding, and the edges represent relationships between these embeddings. And these relationships are largely based on Euclidean distance between them. Each node in an hnsw graph index has a set of friend nodes, and it maintains its own friend list. To better understand hnsw graph traversal, let's first look at NSW search traversal. And NSW stands for navigable small worlds, which means we're not at the hierarchical stage yet. With NSW, we start at an entry point node, and then we go through all of its friend nodes, and we figure out which one is the nearest neighbor to the query vector. So for all the nearest neighbors of this point that we're searching at, which one of the friends is closest to our query vector? And then we stop at a local minimum. So once we're at a node that is closer to our query vector than all the other nodes that we're seeing, then we stop. When you're doing hnsw search, you typically want to start at an entry point, which is a high degree node with many connections. And the reason for this is that it reduces the chance of stopping early by avoiding low degree entry points. And this kind of makes sense because if you start at a low degree entry point, it's possible that the local minima you find isn't the best local minima compared to what you would get if you had a high degree vertex that you're started with. Now, this does slow down search, but generally the accuracy gain you get by starting with a high degree vertex is worth it. An interesting thing is that for NSW search, you don't always start with a high degree vertex. You could also start with a low degree vertex, but for hnsw, you typically start with a high degree vertex. The number of connections on your entry node can be specified, and a higher degree improves recall but slows down search speed. hnsw improves on the NSW algorithm by adding additional layers, or this hierarchical set of layers. And the index is split into these layers, and the top layer typically has the longest distances between nodes. And the lower layers have shorter distances, and they have more friend nodes. You start your search at your top layer, and you find a local minimum. And then you go down to the next layer and find the local minimum there. And then finally, you're at the bottom layer. And when you find a local minimum at the bottom layer, then you found the nearest neighbor to your query vector and you stop. Generating a very large hnsw index can be pretty slow. So it's very important to choose the right hyperparameters so that when you're inserting new data, updating your index doesn't take too long. The hnsw parameters include the number of dimensions, which is just the number of dimensions in your vector embedding. Your EF construction. The EF construction is the number of nodes traversed during graph construction. And typically, the higher the value of EF construction, the better your accuracy, but it's going to take longer to build your index, and your memory usage is going to increase. EF search is actually a parameter that you could pass at inference, and it's the number of nearest neighbors that you explore during the search. And higher values yield more accurate results, but can slow down the search. M is a build parameter that determines the max number of connections per element in the graph. And just like EF construction, the higher the M parameter, the better your recall is going to be, but your memory usage is going to increase as well. So when should you use hnsw? You should use hnsw typically when you have very high dimensional data. So think hundreds or even better thousands of dimensions. And it's very efficient at approximate nearest neighbor search. It's basically one of the best algorithms we have for ANN. It could handle large scale data sets. It could scale extremely well. And it works well with real-time and dynamically changing data. Yes, we have to worry about this index that takes time to build whenever we're adding data, but this index is more manageable than something like IVF. For IVF, we actually have to train our index. With hnsw, we just have to wait for it to build whenever we update our hnsw index with new data. An inverted file index is a data structure that maps vectors to their locations. And it does require training, but the advantage of IVF is that it greatly reduces scope through clustering. What that means is, whenever you insert data, it uses k-means clustering to partition your database vectors into k different clusters. And then instead of searching your entire database when it's comparing document vectors to query vectors, it only searches the n closest partitions to your query vector. And you could determine the number of clusters or partitions that you search at runtime. And in terms of its structure, it consists of an index that links vectors to their corresponding partitions. That's why it's called an inverted file index. And this is extremely efficient because we're not actually searching every single vector, we're only searching these partitions. And this is an order of magnitude faster. If we'd like to visualize our index, it would look like Voronoi cells and centroids. So vectors are arranged in Voronoi cells, and that's what you can see on the right, where the Voronoi cells are bounded by white lines, and the centroids are white circles. And how this is constructed is you start at these centroids and you expand out from them unilaterally on all sides, and basically the white lines are where these boundaries meet. The query vector is represented by the green star here. When we're making a search, our cells that are chosen are determined by our query vector and our probe parameter. So our search is restricted to the cell the query vector lies in and the nearest centroids of the surrounding cells. So when we make a search, we take our query vector, we find the n closest centroids, which is determined by the n probe parameter, and then we only search the cells that encapsulate those centroids. For example, if we have a probe parameter of 3, we grab the 3 nearest cells to the query vector and only search the vectors inside those cells. And the benefit is that it massively reduces search scope and increases retrieval speed, because suddenly we're not searching every single vector, we're only searching a small subset of these vectors. Product quantization is based on the idea that the vectors we insert into our vector database have thousands of dimensions and take up a lot of memory. But by compressing these vectors, we could save a lot of memory at the expense of recall. And the accuracy we lose by compressing these vectors often isn't that much. And how this works in practice is we split each vector into n splits subvectors, and then we use k-means clustering to create centroids for every subvector. And these centroids can be used to map the quantized vectors into an approximation of the original vectors. And this gives us massive savings in memory, 97% plus. It's not very effective in terms of pure product quantization, because if we just do product quantization, we still need to do a flat search when we're doing inference. And there has to be a better way. And that is combining IVF with product quantization to get ivfpq. ivfpq compresses vectors with product quantization before applying IVF. It does require training, just like IVF, and our parameters are still these n clusters, which is the number of Voronoi clusters to create. But we also have these additional parameters of n splits and n bits. N splits is the number of subvectors to split the vectors into, and n bits is the number of bits after compression with PQ. And these are going to determine how much we're going to compress our vectors before creating this IVF index. So these are things to consider with ivfpq, but ivfpq has massive advantages. One is that it yields a great reduction in memory usage because we're using PQ, and has a much lower search time with great recall because of IVF. And it's well suited for high dimensional vectors and fast nearest neighbor search. It's just really good at both reducing your memory and increasing your search speeds. It has a lot of the same benefits of hnsw, but at a much lower memory capacity. Choosing an index can be difficult because not only do you have to choose the specific index, but you have to also choose the specific parameters of that index in order to minimize latency and maximize accuracy. In general, some heuristics that you could use to choose an index are, if you don't have a lot of memory requirements and the size of your data set isn't very large, then just use a flat index. It's going to be very simple, insertion speeds are going to be quick. It's going to be very accurate, and you could use this as a baseline to compare against. As your index gets larger, let's say to around 10 million vectors, depending on your memory requirements, you could use hnsw, and hnsw is going to be extremely fast. The retrieval speeds are extremely quick, but it does use more memory, and it can handle very high query volume. So it's a good option for most medium-sized workloads, and that means 1 million to 10 million vectors, for example. Once your dataset size increases to above 10 million vectors, suddenly memory becomes a problem, and ivfpq solves for that. You still have a lot of those same benefits of hnsw, which is quick retrieval speeds and relatively high accuracy, but you do sacrifice indexing speed in that you do have to train your index before you could actually use it. So the vectors that you train your index on don't have to be your exact dataset vectors, but the distribution has to be the same. So these are the kinds of trade-offs that you'd likely be looking at when you're choosing an index. And in general, yes, it's really good to try multiple indexes with different parameters and see what kind of accuracy and latency you get. But if you're just getting started, using these heuristics is hopefully going to get you on the right path. Some final thoughts are, indexes are absolutely crucial for performant vector similarity search, because at some point you do have to sacrifice a little bit of accuracy for massive latency gains. And there are many approaches with different trade-offs. There are many indexes that aren't supported by KDB.AI that I didn't cover here, and some that are. For example, temporal similarity search I didn't cover in this video. And your specific choice of index and query type depends on your specific use case and requirements. Your distribution might be different, the size of your vectors might be different, your machine might be different with different memory requirements, for example. So you have to consider all these things when you're choosing an index that's right for you. And another thing to consider is that vector databases are continuously getting better. So, for example, something that took 100 milliseconds 3 months ago might take 10 milliseconds now. So vector DBs are getting better constantly, and it's getting easier to both manage your indexes, insert millions or even billions of vectors. Search times are getting faster. In general, vector databases are getting better, and I'm really excited to see the progress that is being made on vector databases and indexes in general. And that's it. I really hope this video demystified indexes a little bit and made it a little easier to choose the right index for your use case. And I'll see you in the next video.